Hello, Malban calling, and I'm again a little bit sickly, so I have some time at home, and I thought I haven't done a PiTrex video in a long time, and so I'm starting with one. I'm switching on my Vectrex with the Pi in it.
PiTrex.
There it is. Actually, not all too much has been done in the last, nearly half a year. I paused a little bit because of Vectrex, which still isn't finished, and I only did little stuff, but much little stuff, which is under the hood. Two things you already noticed. I wrote a little routine to output digitized audio. This was the start of the PiTrex, and I've written a little YM player. In the background you are now listening to Gianna Sisters. This probably won't last because I don't think we get the rights to listen to that song, but it's just a test. Here you see the current menu. One new thing is at the bottom. From the Vectrex C library for the PiTrex, you can now also print raster text. This is a message on the bottom, and on top there is the menu. It's probably more or less the same than the last time. Battle Zone, I haven't done anything with it yet, so it doesn't work. Linux, this doesn't work either. The thought was to have this one as a boot menu, so you can either run Vectrex or PiTrex games from it, or start Raspberry Pi, the Linux that is on it. But this does not work yet, and I'm not sure if it ever will. The boot sequence of the Raspberry Pi is rather involved, featuring separate partitions with write and no write access with different file systems, and so on. This is rather complex, and yes, I'm not sure that I will work further on it because it seems rather stupid to me. But they probably had many reasons to do it like they did, but I just not smart enough to. Yes. Anyway, then this one is also new, Gyrox. Probably seen it on a Facebook group. It was converted to the new Vector PCB unit done by Fred Konopaska. Alexander, what's his last name? I can't remember. Alexander did a version for that, and in a couple of hours I also could convert it to the PiTrex, and we just can look at it. This is Gyrox. The default settings are a little bit too large, so I have to go to the menu and enter and change the size. Oh, that's bigger. I want to make it smaller. Smaller, and here smaller. So this is more or less, I think, what's supposed to look like. Here you can steer this spaceship, and you can fire and kill these. This one I can't anymore. There's no sound to it yet, but I think this is a complete Gyrox. At the bottom you see a frame counter about here where the ship is now. If it's supposed to be 50, it's either 49 or 50. You probably can see it right. And points here. Well, you can get points when you shoot at these things. It's a very little game, a tiny little game. The C source code is only a few lines long, but it works well. Going back to the main menu is pressing all 4 buttons on the joystick at once. So you can go back to the menu at all times. Tail gunner I've already shown you. Asteroids I've shown you, nothing new there. Then the Vectrex emulation. There are 2 Vectrex emulators at the moment, Vectrex Direct and Vectrex Emulated. both are, well, back exports, but the direct version is the one where the wire is not emulated, but all wire calls are going directly to the Vectrex wire. So the emulation step of the wire is passed through, so to say. This looks rather well for now. I've also written a little loader. Here you can choose what games to look at. Spike. I haven't tried Spike. I'm wondering if the speech is going to be alright. Let's start that. So this is actually on the Pi an emulated Vectrex running its output on a Vectrex. It's, well, yes. It looks at the moment rather good. Before I had much trouble with a... Digitized speak works. The text looks rather good now. That is due to cheating. It was not possible for me to emulate cycle exact enough to output rastered text or any rastered graphics. The thing is, one cycle on the Pi is 1 nanosecond. One cycle on the Vectrex is 666 nanoseconds. And the shortest timer you can get on the Pi is 1 microsecond or 1000 nanoseconds. So that is one problem. You do not get exact values with a timer on the Pi. The other one is, in order for raster text to work, the assembler instruction on the Vectrex have to be the exact same timing as on the Vectrex. Because the way raster text is realized, it goes forth one way, puts values into the shift register, which are transformed to raster dots, and then it goes back. And this goes back uses a different loop or different instructions, assembler instructions, which on the Vectrex result in exactly the same cycle count. And it is not all that easy to discover when it's a loop going back in raster printing, or if it's just a normal loop, because there can theoretically be all kinds of instructions, and to have that 100% alright, you have to ensure that each and every assembler instruction has exactly the same length as on the Vectrex. And that is, well, I wouldn't say impossible, but very hard. For one thing, you cannot use the timer. That's what I said before. You have to have, if it's 100% correct, busy loops with known cycle length on the ARM chip. On the other hand, if every assembler instruction is the same length as on the Vectrex, you don't have any speed overhead where you can do other stuff. So it will be really slow, because then the emulator is exactly as fast or as slow as the Vectrex. So that is nearly impossible in my opinion. Well, what I did is I caught the print string instruction of the BIOS and print stringed all strings on the Pi side. So this gives these perfect looking rasterized strings. I know it's not perfect. Every game or cartridge which uses other rasterized print instructions will not work as good as these print string functions you see in the original versions, but well, for the moment it can't be helped. It does not look absolutely awful. I tried to do the timing really good, and you can still read the text, but it's a little bit grisly if it's full emulated. At the moment I cannot show you. I haven't got a binary ready on it, but yeah, it looks similar as in the last video, so to say. For the Vectrex direct, to go back you have to press the reset button, then it goes back to the PiTrex menu. Yes, so and then there's this Vectrex emulated. You probably can see it already, it's quite a lot slower. This one here is fully emulated, it's not using the Vide directly. So what follows is that every vector you see here is printed as an own line instance. So in the beginning, the start screen, you see these dashed lines. Each of them is in this version printed as a separate line. And this can get out of hand really fast. This is why the intro is so slow in comparison, because there are so many vectors. On the real vectors, these are lines which are put out dashed. It's 4 lines or 8 lines, the dashed lines, and in this version it's, I don't know, 40, 50, 60. Anyway, this is the disturbance in the force you saw up here. This is due to the Vectrex I'm playing on. This is a so-called cranky Vectrex, and the upper left corner is, so to say, difficult. Yes. So you see, the full emulated one is, if it doesn't have to display too much text, it's also fast enough. And there are little disturbances here because I haven't looked at the code anymore. These are mostly due to this Vectrex and things not optimized yet. But even this version in normal gameplay is usually fast enough, and it can perhaps be even faster than the original Vectrex. So with this version it is possible that flickery games on the original Vectrex would be, well, non-flickery. This is a known Mindstorm bug when the memory is zeroed out and not filled with ones. You might have heard of that before. Anyway, in this version, since it's truly completely emulated, 4 buttons take you back to the menu. Yes, that is my current stand on PiTrex. I'm sure the others, Kevin and Graham, have more to say, but I just wanted to show you my current stand on it. And yes, I think I will do a very short video also showing some code. So see you in, well, for you probably a few seconds. Bye. Hello and welcome back. Now we are on the Mac side of the Pi. What you see here listed, this is my little card that goes into the Vectrex with the file system where the Pi starts up. The most important things is boot code. I think this is what started first, then this one goes to start elf. In between it reads this fix up and config text, and at some stage it goes to the kernel.img. This is the one that loads my stuff, this kernel. And from there the loader is loaded, and the loader displays all .img files. It finds, no, it does not. It displays the files I say it has to display. We are looking at that later. And the loader also loads all these img files and starts them. Actually, each of these files could be also the kernel img, and they would run from startup, so you don't have to go through the menu. They are compatible with the kernel. Except the Linux startup should be Linux img, and this does not work due to reasons I'm not 100% familiar with. but which I try to explain or at least talk about in the other video. So Linux does not work. The other files that might be interesting, the actual YM music file is this one here. This is also loaded from disk. The PiTrex sample is also loaded from disk. And all the Vectrex games that can be played are stationed in this directory Vectrex and are also loaded. So everything you see in the PiTrex or you saw in the PiTrex menu is loaded from disk. Actually, my setup is a little bit complicated and it could probably be made much easier, but well, never change the running system. I usually insert the card and my Mac shows it as no name, and I copy it from a directory I have here on the other side, which I call Ubuntu 64. This my setup. I have an emulated Ubuntu 64 here with parallels, and I do all my PiTrex work on there. And the make files automatically copy the resulting files into this directory of the Mac, and from here I copy it over to there. So it is a little bit complicated setup, but if you don't change the files all too often, it works and is stable, and I can copy the image, and well, everything is fine. Anyway, the working setup of mine is I have a working chainsaw for the RM build, RM non-ERB object. This is standard bare metal Pi development environment. Actually, I got on my Linux system. These are the directories. I have got a top make file which makes all of the below, and yes, and in each of these directories is also a make file, one for bare metal and one for Raspbian. This actually compiles the games for the Raspberry Pi operating system and runs them on the Vectrex from there. But actually, I haven't looked at these make files for quite a few months, so I'm not sure they actually work anymore. I usually use only the make file for bare metal. Here we are in the Gyrox directory. I can show you for now the main file. I renamed it to C extension. This is a Gyrox main file, a bit boring, the header, but probably for you. Sorry, excuse me. For you, because it was written by a German guy and I'm also German, so I did not translate it, because for me it was okay. I changed the program slightly to be 100% C compatible, because it was a mixture between C and C++, I think, or whatever. Anyway, these are the structs, some defines. This is a fast sign table, and this is a new function of mine where I initialize the variables, because in the original they were initialized in the, were they in the type def struct? Oh, I don't know. Anyway, it didn't run as it was in the beginning. Then I've got two additional functions, move to relative and line to relative, because the source code was based on the fact that all lines are moved absolutely on an oscilloscope it was written for. And at least for the objects and the text, it makes on the Vectrex much sense to do relative movement. Otherwise, it would zero well with every vector. So I've got some relative movements here. The move function more or less is the original one, more or less, because there's some translations had to be made because of the coordinates. The draw character is more or less the same, respectively the move to relative. So are the draw objects, move relative here. Collision is exactly the same. Collision bullet is exactly the same. Add bullet, update ship. Somewhere here is the button stuff where you can fire. This I did for the Vectrex. And everything else is the same. Update rocks, add enemy, update enemies, draw field. These are the little corners. They look a little bit different. This is function because of the relative movement. We didn't have any constraints in the C compiler, so this is a little constraint function, so the source code stayed the same. This actually is more or less the actual game loop. The joystick is questioned here, and well, this is all. This is a complete source code for Gyrox. This actually is the game loop, but this video function above here is called right here, and this actually does all the game logic. And here only the points and the frame counter is displayed. Yes, that is Gyrox, very quick. I'm going to show you the PiTrex loader as it looks now. The loader which, with a menu which is displayed right from the start. This is also a very short program, as you can see. This is all. This is actually the main program. The kernel more or less drops in here. This initializes the bare metal libraries, Vectrex in it, and the init for the PiTrex actually. This little function plays. Yes, this plays the wave file. This loads the YM file. This plays the YM file when in the boot menu, and this is an endless game loop for the menu. You have the typical Vectrex wait recall. Then we read buttons and the joystick. We set a brightness. We give out some raster text at the bottom, and the boot menu is displayed with an own function, which is above here. This is the boot menu. Here you see the text. It's printed. Joystick is questioned, moved up, down, and then load and start is executed if you press a button. You see these are the files which are loaded actually, and the little load and start function is here. Well, file open, and somewhere here proc start. This actually starts the image file that was loaded from the address it was loaded to. Really everything quite straightforward. I'm going to boot up the Pi now so you can see what is happening. I'm going down. This is the loader main function, and somewhere, one moment, this is my serial application because I have a connection, a serial connection to my Pi. I'm starting it now. So this is, where is my emulator? There. You can see PiTrex starting, loader starting. This is cool. It doesn't look exactly the same. Yeah, no. This is even before. I told you before, this is the kernel actually above here till here. This is a kernel.img, and from below this point on, it's the loader. I haven't shown you the kernel. It doesn't really matter, but it's working exactly the same way. Here the loader is starting. Loader starting is here. It redisplays the clock values, mounts the file system. Then somewhere between in this V init, I don't know, the UART is a little bit garbled. I don't know what happens there, and I have not been able to debug it correctly, but I wasn't all that interested anyway, because it fixes itself. Anyway, this is here, and then it commences, the YM file is loaded, and now we are actually within the game loop. And I think if I select something, that's Vectrex emulator, direct emulator. Now it shows here loading Vectrex emulator, and it shows again the Vectrex files. And on the Vectrex you can now see that these bin files are displayed, and you can select one. Don't know, does it say anything if I select one? Yes. Now I've selected one on the Pi, and it's, well, now emulation is started. Emulation percent 69%. This is not exact. I rather suspect that the emulator is running at 100% speed, but the cycle counting with catching print string routines is not 100% correct anymore. So I think the emulation is running at 100%, but you do not see it here. That's, well, I might change that in the future so that it's correct. Yes. Anything else? Perhaps a short look at the Vectrex interface itself. These are these 4 files actually. The header file. These are all the public available functions, so to say, that you can use from any C program for the PiTrex. Many functions have to do with with timing. You see these delay cycles, wait mark, measure time, wait full micro, and so on. I don't know if I use them all anymore still, but at one point or another they were quite important for timing issues. These V delay cycles delays the Pi for the given cycles in Vectrex cycles. So one Vectrex cycle is, I said that before, 666 nanoseconds, and usually you wait for 2, 3, 4, 5, 6, 7, at maximum 8 cycles. It does so as exact as possible. Then there's delay nano. This is used by the delay cycles. This actually delays a number of nanoseconds. What is done here is where it goes sooner or later to this macro down here, and this actually executes a sequence of RAM assembler instructions. And it loops them, and one loop of these is exactly 4 cycles for the RAM, and the ARM cycle is 1 nanosecond each. So theoretically, this wait nanocycle can do waits up to 4 nanoseconds exact. It's not always that exact, because there's overhead to call the function and so on and so on. So it's not exactly 4 nanoseconds, but well, you get the point. And other much used functions for timing are these set and wait mark. The gist of the problem is that I cannot the most exact timer on the Pi is 1 microseconds, and I often have to wait, well, more or less exact. On the Vectrex you already see a difference if it's half a microsecond off. So even if I cannot wait for the exactly 666 nanoseconds the Vectrex has for one cycle, I want to know how many cycles I wait, and the main gist is I want to wait for exactly the same time 2 or 3 times in a row, so I can align my vectors. And what this thing does, set mark, this sets an internal variable for the actual timer of the ARM, and it waits till one microsecond till the timer just switched, so that it's right at the start of the 1 microsecond count, so to say. And the mark end waits for the number of microseconds since the mark was set. So if I start set mark and wait mark end for 2 microseconds, then, well, plus minus a few nanoseconds, we exactly wait for the microseconds. And not for 1.5, 1.3, 1.4, but for 1.001 or something like that. So at least the difference timing I get really exact with these two functions, and that is important on many occasions. Well, this is similar. This just waits till the timer just jumped, measure time, and so on. And these are actually the normal Vectrex functions that you know and love. Set brightness, these move things and print things. These are actually line draws or line moves in 32-bit, which are translated to Vectrex 8-bit coordinates. And set refresh, zero wait, wait recall, recalibrate, reset integrator offsets, reset detection. This we can detect a reset on the Vectrex because the via input-output states change when a reset happens. At the moment this only works for the direct emulation, but I want to implement this also for every other function. The gist is that it does not work now is because I do the timing of the Vectrex still with the Vectrex via timer, the timer T1, and I want to change that, the whole function interface, to use a Pi timer. The thing is, if I use a Vectrex timer and a reset is done on a Vectrex, then the timer never reaches the end and the program halts, it stalls, it crashes, so to say, if I do a reset on the Vectrex. But if I do the timing on the Pi side, then I do not rely on the timer of the Vectrex, and I can detect the reset. There are other advantages to that. This is a next major change I make in the Vectrex interface, but yeah. Then the reset detection will also work. This is the calibration, read joystick, digital, analog, print string. This is a vector print string routine you see in the menu, and this is a print string raster I see in the menu. And there are also more or less internal functions which I only use within the interface. The set scale and move immediate and draw immediate. I use these mainly within the vector drawing, or the vector text drawing, because it's, still is faster not to use these 32-bit functions. Then there's some PSG stuff for the YM player and so on. The rest of the file actually is a whole lot of defines for VR ports, for wait states. We are in freestanding, so in bare metal. These are all wait states defined, which we have to wait after we set some via values, delay cycles for different needs, and so on. These are only just defines coming down here. Yes, the interface itself, it's not, it's C code. I won't go through it. It's rather boring, so to say. You can look at it yourself. What might be interesting is the vector font. These are actually more or less exports from Vide, from a char set I've got there, and I replicated more or less the draw VLP function in this short code here. This is actually a draw VLP, and a character is input in there, and then it's drawn on the Vectrex. Well, with this code. Yeah. And this is actual print string, which calls, well, the vdraw VLP for each of the letters. The raster data is actually, this is an export of the Vectrex BIOS, and this is, well, the C version of the Vectrex BIOS string routine. And yeah, this is then the print raster string version on the Pi side. Yes. Here you see that somewhere over the rainbow. I do not see it immediately, but somewhere in here I make use of these exact timing things. This delay cycles, this raster weight, for example. This is the exact weight. This is more or less the 18 cycles Vectrex waits for its raster, for its shift cycle to finish. It's defined as 16. I probably have to redo my internal values because this should supposedly be 18 and it's 16 and it works. So the timing values are not 100% correct, I guess. Yes. I don't know what else to say. You can look at, if you are interested into one of the make files. These make files are all handmade, and at least for the time being, it stays that way. Each one of these directories is in itself complete and compiles the complete img file. So I do not reuse or build libraries at the moment. Each one of these compiles all the stuff it needs. And it does so also in, well, extensive stages. At first, I built all assembler sources, all .s files, so to say. Then I built all .o files, and then I assemble all these object files with library files I need to one. Where's the output one? To the, in this case, Gyrox elf img. The elf then is removed later with this step here. Then for debugging purposes, the image itself, it's dumped again as a source image, and then I copy it to my Ubuntu directory on my Mac, and then it's finished. So for the time being, this is an exact compile sequence. At the beginning of my ARM compile stages, it was necessary for me because I wasn't used to Linux or Unix environments anymore, and makefiles and so on. And well, perhaps today I would do it differently, but right now this is the way it is and it stays. So this is the coding side. Compile itself is done from, well, from the command line interface, from the shell. This was probably boring for you, but I just want to get it out in the open, and perhaps it was interesting, or perhaps not. Anyways, thank you for watching and listening. Goodbye.